Hello everyone and welcome to our channel. So today we're going to explain about the Michaelis Menten equation. So first, let's review the idea that enzymes are catalysts. They make a reaction go faster. Enzymes are catalysts, which means they will increase the rate of conversion of some biological molecule to another by lowering the activation energy that is required to allow a specific reaction to proceed. And this process is what we call an enzymatic reaction. So, this enzymatic reaction is actually used or applied by drugs. Drugs works by inhibiting or by activating the enzymes inside the body. So now we're going to talk how actually enzymatic reaction proceeds. So enzymatic reaction can be thought as the combination of substrate and an enzyme. So we'll take, for example, this is our substrate, while this is our enzyme. So what actually happens is the substrate will bind to the active site of the enzyme and thus forming a complex we call enzyme substrate complex. So this is our enzyme substrate complex. This enzyme substrate complex can undergo a chemical change or rearrangement that will actually produce a short-lived intermediate enzyme product complex. This is an intermediate enzyme product complex. Since it is only short-lived, meaning that it will rapidly dissociate, yielding products and enzyme. So this is the enzyme and this is our products. And this enzyme can actually be reused or to catalyze the next enzymatic reaction. So we have our enzyme E plus our substrate yielding our enzyme substrate complex that can form into our enzyme product complex, which is a very short-lived complex which will then dissociate into enzyme and product. And this enzyme can be used to catalyze a new reaction with a new substrate. And now let's look on how enzyme actually converts substrate into product. We are going to discuss the kinetic of that conversion product. The kinetic refers to how fast the process occurs. And now to understand this, let's imagine we have 3 beakers. Beaker 1, beaker 2, and beaker 3. Now inside these beakers, we will add known quantity of enzyme to each of the beaker. Enzyme, enzyme, enzyme. And the next step is we will be putting different amount of substrate to each of the beaker. For the first one, we will put a little bit of substrate inside. For the second one, we add a little bit more, and for the third one, we'll put a very high amount of substrate. Now, when we have enzymes and substrate, enzymatic reaction will happen. The enzyme will convert the substrate into product. Next, we will be measuring the rate of reaction where the product was formed over time. So actually, we will see that the first beaker with a little bit of substrate will be relatively at slow rate formation of product, while the middle beaker, the second beaker, it will have high rate of reaction compared to the first one. And finally, the third beaker will have a very high rate of reaction compared to all these 3. So what can we actually conclude from this is the reason why this third beaker have higher rate of reaction compared to the first and the second beaker is because when we add more substrate, we will get an increased speed of formation of the product. High concentration of substrate essentially serve to maintain the substrate bound to the enzyme. To maintain the substrate bound to the enzyme. Here, the flux of substrate through the enzyme is maximal. Flux meaning the process of flowing, where as soon as the enzyme product complex dissociate, as we have mentioned earlier, the enzyme product complex will dissociate to enzyme and product. Enzyme can be reused. So, when this enzyme product complex dissociate, yielding a free enzyme and a product. As soon as the enzyme product complex dissociates, when they see this free enzyme floating around, another substrate, which are also free floating around the system, will actually bind to this free enzyme. So imagine this first beaker, we have one enzyme and one substrate. When this substrate binds to the enzyme's active site and then forming enzyme product complex and then dissociating, there is no substrate available to bind to it. That is the reason why the rate of reaction are much slower. So this is the reason why the reaction in beaker 1 is much slower. And for the third beaker, the rate of reaction is much higher because we have a lot of substrate available inside here. So when one substrate, we have substrate 1, when substrate 1 binds to the enzyme, it will dissociate into free enzyme and products. And then we have another available substrate 2 in here, and it will bind to the free enzyme. And then we have substrate 3 and 4, and this process will repeat itself, and this is the reason why the rate of reaction of beaker 3 is much higher.
Okay, next, let's go on with our main topic today is Michaelis Menten kinetics. First, let's plot a graph of the rate of enzyme reaction versus the concentration of substrate. This is for showing the expression of enzyme activity. Here we work out the rate of formation of product as the function of substrate concentration. First, the rate of formation of P plotted on the y-axis, which is formation of P here called as V for velocity. So that means how quickly P was being formed. So we label here as rate of reaction. And for the x-axis is concentration of substrate. When we have get an experimental data, when we do the plot graph, we will exactly get this kind of curve, which is called as hyperbolic curve. At this part, the reaction is speed up, follow the first order kinetic, and it's become flattened here until at one point we call F, zero order kinetic. For this graph, it relates the initial reaction rate to the concentration of substrate. The maximum rate of the enzyme, it can be achieved at high concentration of substrate. When the enzyme is saturated, we call as Vmax. Okay, next, the Michaelis constant, which is Km, is the concentration of substrate at which reaction rate is half of the Vmax. So basically, we can guess here Vmax over 2, and then we extrapolate here, and we can get the value of Km. Okay, next, let's proceed with the Michaelis Menten equation. We come up with the equation which is V naught equal to Vmax times the concentration of substrate over with the Km plus concentration of substrate. Now we want to justify that the Km is when the Vmax is become half. From the equation, we can justify it by the mathematical approach. Let's say at the same point of the graph, Km is equal to the concentration of substrate. we want to justify Km is when the Vmax being half. So to figure out where there is the point on the graph, let's change Km to the concentration of substrate. Okay. This from equation, we substitute Km with the concentration of substrate, which is it will become V naught equal to Vmax times to the concentration of substrate over concentration of substrate plus concentration of substrate, and we solve it by mathematics. It will become V equal to Vmax substrate concentration equal to 2 concentration substrate, and then here we can cancel concentration of substrate at the up and below, so it will become V naught equal to Vmax equal over 2. So here we can justify that when V naught equal to Vmax over 2, Km is concentration of substrate. We can get the value of Km on the graph. Now let's talk about what is Michaelis constant really represent. From this equation, we have to know that the value of the Km should be less than concentration of S so that the Vmax could be achieved. The important point for you to understand is the system cannot reach the Vmax until concentration of substrate much greater than Km. Now we go back to the graph plotted just now. At the Vmax, the condition is the enzyme is saturated here. The only way to increase the Vmax is by adding the enzyme. So the curve eventually will be like this. It will shift upwards and the Vmax will be greater. Now we also can get straight line graph by inverse this kind of hyperbolic curve to the straight line graph. This graph we call as Lineweaver Burke plot. So now we look at back to the Michaelis Menten equations. We just inverse the below one to the up. It will become Km plus concentration of substrate over Vmax times to the concentration of substrate, and then here we divide into two components. It will be 1 over V naught equal to Km over Vmax times to the concentration of substrate plus substrate concentrations over Vmax times to concentration of substrates. As we can see here, there is concentration of substrate at the up and the bottom, so we can cancel off. So it will become 1 over V naught equal to Km over Vmax times to the concentration of substrate plus 1 over Vmax. Consider as Km over Vmax as one thing, we could label it as C. So it will become 1 over V naught equal to C times 2 1 over concentration of substrate plus 1 over Vmax. Don't you realize this kind of equation is resemble the equation of straight line y equal to mx plus c. So here we can know 1 over V naught is y, c which is Km over Vmax is the slope of the graph, the x is 1 over concentration of substrate, and the y-intercept is 1 over Vmax. So we come out with y equal to mx plus c, y is 1 over V naught, the slope of the graph Km over Vmax, x-axis is 1 over concentration of substrate, and y-intercept is 1 over Vmax. Okay, so next we translate all the information that have come out just now into the graph, we will get this kind of straight line. The y-axis is 1 over V naught, and the x-axis 1 over concentration of substrate. The slope of the graph, which is Km over V max, and the y-intercept is 1 over V max, and the x-intercept is negative 1 over Km. So from this graph, it's easier to identify the value of V max and the Km.
So for the question, find the ratio of a concentration of substrate to Km when the velocity of an enzyme catalyzed non-inhibitor reaction is 10% of V max. So first, for the formula is V naught is equal to V max concentration of substrate divided by Km plus concentration of substrate. So first, let's say V max is equal to 10. V max is equal to 10 because of reaction is 10% of V max. Then V is equal to 1. So just substitute into this formula. V is 1, V max 10, concentration of substrate Km plus concentration of substrate, but they still have two variable. Still have two variable. So number 2, step number 2. Let's say concentration of S is equal to X and Km is equal to Y. So substitute into this formula. 1 is equal to 10x divided by y plus x. So by using a simple mathematics, y plus x is equal to 10x, then y plus x equal to 10x. Then we got the equation. And number 3, subtract x at both sides. So we will get y is equal to 9x. Then step number 4, divide x at both sides. So y over x is equal to 9 over x, then x over x, cross cross, then y is equal to x over 9 over 1. So the question is find the ratio concentration of substrate to Km. So this one you just change like this. So the final answer is Km is 1 over 9. Next question. Assuming all other reactions remain constant and that the reaction is allowed to proceed to equilibrium, how would the reaction substrate to product be affected by the addition of an enzyme catalyst? Okay, as stated before, we have mentioned that the only way to increase to increase Vmax is by adding more enzyme. So in the question, it says that how would the reaction substrate to product be affected by the addition of an enzyme catalyst? Is increase total product form? No. Neither increase reaction rate or increase formation of product? Not really. Both increase reaction rate and increase formation of product? I think no. So the perfect answer is increase reaction rate. C. Thank you.